Okay, thank you very much. And I'd like to thank the organizers for this opportunity to present my joint work with David Jekel and Anshu Nirbay. So as with so many objects in non-commutative geometry, we begin with a question of con, namely, what is the quantum automorphism group of a space? And so in non-commutative geometry, that space may be quantum or it may be classical. And the beautiful surprise is that even for classical spaces, even classical spaces can admit quantum symmetries in addition to and including their classical symmetries. And so quantum permutation groups are compact matrix quantum groups which arise as quantum symmetries of spaces, finite point spaces, sets with finitely many points. And in development of an answer to that for this case, Wang, who was a student of Riefel, developed the theory of quantum permutation groups. And so the motivating question for our project was, do quantum permutation groups admit quantum metrics? And so, of course, if you can define a metric on a quantum permutation, then you can measure how closely two automorphisms act on a space. And if your metric is the appropriate quantum analog of a Wasserstein distance, then it would give a meaningful way of measuring the cost of moving one state to another under elementary transformations. So in non-commutative geometry, even classical objects can be viewed through an enriched quantum lens. So here is a classical permutation matrix, and viewed as actions on, in this case, a 4-point space. You can view this permutation as being the one that takes something in the first position to something in the third position. And that's also an example of a quantum symmetry. But here's another example of a quantum symmetry on a 4-point space. And so this is where you can see the quantum nature. So here, whatever's in the second position gets taken a little bit to the first position and a little bit to the second position. And, well, matrices are finite dimensional examples of bounded operators on a Hilbert space. And so our quantum permutations matrices can also take as entries projections. And so not only do we have extra symmetries that appear in the quantum lens, we also contain the classical ones. So another motivation to study quantum permutations is because they're also a basis for understanding quantum symmetries of classical graphs. And this is due to the work of Biane and Voiculescu. And in one of their notions of the quantum symmetries of a graph, a quantum automorphism of a graph is, so this is the adjacency matrix for this graph. So then the quantum symmetries are those quantum permutations that commute with the adjacency matrix. And so therefore, if you want to understand the quantum symmetries of a classical graph, which of course, if you're working with truly quantum algorithms or you want to extend to the quantum setting some classical algorithm, then understanding what its symmetries are in the quantum world could be useful. And the surprising thing is, so these are classical graphs, And one of these graphs admits quantum symmetries, and the other doesn't. So the foundation of non-commutative geometry is built on the Gelfand-Naimark theorem. And this morally says that all is morally built on unital C-star algebras, and that those can be viewed as quantum analogs of compact Hausdorff spaces. So a unital C-star algebra, it's a Banach algebra. It's equipped with a star operation. It is conjugate linear, involutive, anti-multiplicative, and most importantly, the star operation is encoded in the norm. And so some foundational examples include the complex numbers C of x for any compact Hausdorff space, complex valued matrices, and B of h for any Hilbert space. And so this is why morally all C-star algebras, unital C-star algebras, are quantum analogs of compact Hausdorff spaces, because all the unital commutative ones are star isomorphic to C of x for some compact Hausdorff space. And so by analogy, for all the non-commutative algebras, there exists some quantum space out there for which our non-commutative algebra is C of x. And we'll see that same theme with the quantum, with the compact quantum groups. So this brings me to how does one motivate the notion of quantum symmetries for a finite set? So if I take a finite set, then the group of automorphisms is isomorphic to the symmetric group, and that naturally acts on this endpoint set via permutations. And so the natural way to associate C-star algebra to this is to take the projections. And if you have generators and relations, then you can generate a C-star algebra under certain conditions. And if you move to the wider non-commutative world, then more generally, projections are idempotents, they're self-adjoint. And so here we add the condition that if we use this indexing and view these generating elements as entries in a matrix, then along the rows and columns, we each get the identity. And so we can view this as the, in the first case where the projections commute, then that's a symmetry group of a finite set with no extra structure, versus if we allow ourselves to take projections that are non-commuting, then we have the quantum symmetry group for a finite set with no extra structure. So the theory of quantum symmetries for finite sets is due to Wang. And it turns out that for up to 3 points, the two notions coincide. And then it's at just n equals 4 when the quantum symmetry groups are no longer finite and they're no longer classical. And one way to see this is we can again leverage this sort of universal property that this particular C-star algebra has. So we take the C-star algebra generated by two non-commuting projections, and so we can consider a star homomorphism from our quantum permutation group, which sends each of these, the generating elements indexed by ij's, to the respective entries of this matrix. And so since the C-star algebra we generated is non-commutative, then therefore our quantum permutation group must also be non-commutative. And you can see here very easily too how the conditions on the rows the rows and the columns are satisfied that they all sum to the identity.
Can I ask one more question? So for, as you said, like for n greater than or equals to 4, this would be different from the usual symmetry.
Yes, so that there are other, so that if you take this like same game and you have like these restrictions on the relations, then it turns out that you end up, when you solve for them algebraically, having things that have to commute with each other. So a quantum permutation group, like so many things in non-commutative geometry, has an underlying unital C-star algebra. And so here the underlying unital C-star algebra is the one given by the C-star algebra generated by these elements subject to these relations. And the quantum permutation groups are a special example of compact matrix quantum groups. And so in the more general setting, these relations might be a little different. And again, what is really nice about the quantum permutations is that they aren't just some abstract thing that hovers outside of the classical world, that the classical world is contained in the quantum world. And so this, these relations, which can be represented as entries in an invertible matrix, with the entries being in the C-star algebra, if you take your solutions in the complex numbers, then you will get a classical group. And if you take them in matrices or in bounded operators on a Hilbert space, then you will get a quantum group. And so this is another reason, so for the C-star algebraicists in the room, why these should morally be viewed as quantum automorphism groups of finite spaces is because this is the biggest compact quantum group acting on finitely many points that leaves the counting measure invariant. And so that's a sort of nice structural operator algebraic technicality. So, so quantum permutation groups are more general examples of compact matrix quantum groups, and that notion is due to Voronovich. And so I have my underlying unital C-star algebra. Here is the sort of representative matrix of generating elements arranged so as to encode the relations. So then these entries, they generate the underlying C-star algebra. And so with the quantum permutation groups, we saw that this condition happened to be the rows and columns summing to the unit. More generally, you just have to get an invertible matrix in matrices valued in the C-star algebra. And so that gives rise to other examples of compact matrix quantum groups. And then also there is a unital star homomorphism that generalizes matrix multiplication in a natural way. And so again, driving home this theme of non-commutative geometry as an enriched lens for the commutative world, it turns out that every compact matrix group gives rise or is an example of a compact matrix quantum group. And the way to see this is that we can take as our unital C-star algebra the continuous functions on the compact group, and we can take as the generators. So what this does is that this takes each of the matrices in this compact matrix group, and it just spits out the ith, jth entry. And so we can take the C-star algebra generated by those elements and you can get an invertible, a matrix that is invertible, a matrix over this unital C-star algebra that's invertible, because you're already starting out with evaluating this on invertible matrices. And then here, the star homomorphism is exactly matrix multiplication. And so compact matrix quantum groups truly generalize compact matrix groups.
Just a quick question. So in the Gelfand duality says that if you have like an abelian C-star algebra, it's continuous functions on some space. Is there some sort of, reverse map here as well?
Right. Well, so here we have that these are continuous functions on some compact matrix group. So the group is compact. And so then when it's non-commutative, then by analogy, then those are C of G for some quantum group. So we have this analogy between C of X and X compact Hausdorff. And then here we have C of G, and G being a compact matrix group. So how might we begin to equip quantum permutation groups with quantum metrics? Well, remember that, so that's where I'll look to the work of Riefel. So Riefel started studying and developing quantum analogs of compact metric spaces because he wanted to approximate certain spaces by matrix algebras. And both those spaces and matrix algebras are unital C-star algebras. And in the Gelfand-Naimark theorem, the weak star topology plays a very foundational sort of role. And so Riefel asks, does there exist a metric on the state space that metrizes the weak star topology? And so the whole development of his quantum analog of compact metric spaces is an answer to this question, the different examples that he works through, and the way that those definitions evolve. And I think that for the optimal transport people in the room, then you can see how this is morally a quantum L1 Wasserstein distance. And that's why I started to study optimal transport, coming from non-commutative geometry. And so so this metric was not one that he cooked up himself. It was one that this is actually the Kahn metric. And so Kahn had, in the sort of prototypical setting of C of X for X, a compact spin Riemannian manifold, and there's a differential operator called the Dirac operator, and there's a particular Hilbert space. Then he had shown that the geodesic distance could be recovered by, so you can see this is exactly the same metric, except in place of a more general semi-norm, we have the semi-norm coming from commutators with the Dirac operator, the norm on the commutator with the Dirac operator. And so what Kahn showed is that he showed that this is a metric on the state space, is actually a pseudometric. And not only did he do that in the case of this prototypical classical setting, he also did this for reduced C-star algebras built on groups and with certain conditions on the length function. He defined a Dirac operator in that way, and he also got a metric, and so on the state space. But he didn't ask the question in that work about the topology, and so that was where Riefel picked up on this metric and asked, when can such a metric metrize the weak star topology? And so his development can be seen as non-commutative metric geometry, and that's because every compact metric space gives rise to a quantum compact metric space, and the choice of flip norm is the natural one coming from the metric on the space. And more importantly, for metric spaces, it turns out that that the original space is embedded in the state space equipped with this Monte-Carlo-Ravitch metric. And so therefore, the state space remembers the classical space. But of course, since it's a way bigger enriched quantum lens, then therefore we have a larger space or an enriched lens in which to study the original classical space. And so another example of a classical space would be a fractal like the Cantor set. So even in that case, there are differing quantum metrics on this classical space, but when viewed as, you can equip them in different ways with different quantum metrics. And so the information, so it agrees on the embedding of the original space, but differs on the rest of the state space. And so we can view these as embedded in entirely different quantum compact metric spaces. And the matrix algebras can also be viewed as quantum compact metric spaces. And so one way to do that, here's a semi-norm that does the job. So take the classical matrix trace, build a diagonal matrix with the matrix trace elements, normalize it with the normalized trace, and then take the difference. And so that will give you a semi-norm that does the job. So we saw how morally from the structure that the Kahn refill metric falls really in should be viewed as part of the whole zoo there is out there of quantum Wasserstein distances. And in this program, there was a working group studying this zoo of quantum Wasserstein distances. And I mean, there's a lot of different such distances because there's a lot of ways to introduce non-commutativity into the Wasserstein distance. So for example, through either the choice of cost operator, how you might measure cost, also couplings over what kinds of objects you might have your couplings and how you might couple different things. So those are also ways of, and then there are many different non-commutative answers to each of those questions. And so we have added to the zoo a few new members. And so we wanted to define a quantum metric on the quantum permutation group that recovers the Hamming distance on the classical permutation group. And well, because of course you could define any quantum metric, but if it doesn't recover something in the classical case, then you don't really have a sort of perspective with which to view it that is meaningful. So the Hamming distance on the permutation group, so you can see that it measures the number of elements in the endpoint set on which two different permutations might differ. And so in terms of the entries on the permutation matrices, you could rewrite it in this way. And so since you could view so remember that we were also able to look at, if we extract each ijth entry as a continuous function on a matrix, then we can view this as a continuous function on this product of classical permutation. And so what does it mean to be distance 0? Well, it's distance 0 if the two permutations agree on everything. And it's 1 if they disagree on all of the points. So we decided to take our couplings in tracial states. And so for the people in the room who work in classical Wasserstein distances and know that that setting is in the probability measure as well, every probability measure on a classical permutation gives rise to a state on the continuous functions on the classical permutations. And in Wang's seminal work, he gave a star homomorphism that allows you to quotient, so like quotient out like the quantum permutations, and so that you could, therefore, every tracial state in the classical setting gives rise to also a tracial state on the quantum permutation group. And so then it was natural for us to ask, does there exist a quantum Wasserstein distance on the trace space that recovers the normalized Hamming distance? And the reason that we wanted to consider traces is because one of the problems with, metrics and quantum metrics in general is getting the triangle inequality. And so here, the tracial structure allows us to, so that becomes we're able to overcome that difficulty with the tracial structure, because then we're able to, we define our distances involving projections, and then the projections play nicely enough that we're able to get the triangle inequality. And so therefore, we took our couplings over tracial couplings. And so this is where, before I go on, I wanted to acknowledge that I first met Voiculescu in this room when I was a grad student. I first came to IPAM as a grad student for a workshop in May 2018. I made myself sit next to somebody I didn't know at a talk, so that as a way to force myself to meet more people. And I said, hi, my name is Therese. What's your name? What do you do? And he said, my name is Dan. I do math. And then the next day, actually you said to me, you're like, Voiculescu is here. And I was like, really, who is that? And then I realized who it was. So therefore, I'm very happy to have had the opportunity to be able to learn enough about his work to leverage some of those ideas in this project. So tracial couplings. So we have a C-star algebra and two traces on the C-star algebra. A tracial coupling is a sort of larger embedding von Neumann tracial algebra. And so von Neumann algebras, I guess for me as a C-star algebras person, they're like a more special variety of operator algebra, one that's weak operator topology closed, in addition to usual properties. And this is a tracial von Neumann algebra, then besides being a tracial state, so therefore the state, it vanishes on commutators, so tau of xy equals tau of yx. It's also faithful, and it's also continuous with respect to the weak operator topology. And so the other elements of our coupling involve these star homomorphisms that, so that therefore, when we lift to the larger tracial von Neumann algebra, then it gives us a way to remember the original traces. And so we built heavily on the work of Biane and Voiculescu. This gives natural LP Wasserstein distances on tracial states on universal C-star algebras with specified generators. So you can see from how the compact quantum matrix groups are built that they're universal C-star algebras. So this is especially well suited to these types of objects. And so the couplings that we have, they're given by embeddings into an arbitrary larger Tracial von Neumann algebra. And so it's in this larger algebra that we measure the distances between two copies of the generators. So here's one of our quantum metrics on the quantum permutation group. This one's the quantum Hamming distance. So given two traces on a quantum permutation group, then, so if you remember the structure here of the normalized Hamming distance in the classical case. So here we took the minimum of the projections, and we took the infimum over all the tracial couplings, and I guess I would like, so there are various technical questions like, is the infimum achieved? Is this space even empty or non-empty? And that it's non-empty, directly relies on the free product construction and other ideas from Voiculescu's work. And so this allowed us to, and so in this wider non-commutative setting, then using the tracial structure allowed us to get, overcome some of like these difficulties and even the definition of this distance, let alone whether it's a metric or not. Yeah. So we were able to show that this particular distance is a metric. And not only that if we take the corresponding traces, the traces corresponding to classical probability measures, and we're able to recover the classical Hamming distance. So here is like the classical Biane-Wasserstein distance in this sort of group setting. And here, this is just the usual kind of, coupling with marginals. Here, the cost is the normalized Hamming cost. And we're able to show that they agree when restricted to the traces coming from the classical probability measures. And we were also, so we also had more additions to the zoo. I just focused on the ones that relied on Voiculescu and Biane's work. And this other one, which is a metric, also involved kind of like a quantum L1 norm sort of structure. And this one, which I'll talk about more on the next slide, doesn't define a metric. But amazingly, all of them recover the normalized Hamming distance in the classical setting. So now I'm going to talk about this other sort of cost. So like I mentioned before when I presented earlier, a selection from the zoo of quantum Wasserstein distances, that one of the ways in which one might introduce non-commutativity is through a cost operator. So here our cost operator is some self-adjoint element in this 10 tensor product of quantum permutation groups. And so evaluation on this cost operator is going to give us a notion of cost. And so then how do we couple things? So then naively, it's natural to take, tensors that they have this sort of, structure that recalls that of marginals in the classical case. And so then we get that when we define a cost in terms of the infimum over all of these tensor couplings for evaluation on this cost operator, so we got that it's non-negative and that it's symmetric. It satisfies the triangle inequality, but it's not distance. We didn't get distance 0 on, with the self-costs. So
the self-cost isn't 0, or there are things which are distance 0 that aren't the same?
So there are things that are non-zero that, that should vanish if it were.
They should vanish, but this gives it a positive cost.
Yeah. But I know that a theme in this program was trying to understand cost operators, because of course evaluation as a way of measuring cost is a natural thing to do in operator algebras, and well, at least here's a working example in that direction. So in this program, we had the opportunity to talk with, have many interesting conversations with other program members. And while in conversation with Milad, he asked us, what does distance 1 mean for your quantum metrics? And we didn't know. And so therefore, in direct answer to that question, we went and figured it out. And it turned out that in all of our different distances, that means exactly disjoint supports. So it's also, so taking inspiration from, the history of quantum metrics as developed by Kahn and Riefel, then it's natural to consider Lipschitz elements in, with respect to our quantum metrics. And so we don't know if we have a quantum metric in the sense of Riefel, but at least we have one of the requirements, which is that Lipschitz elements are dense. So we have a good first step in that direction. And so therefore then what we would next need to verify is, does this metrize the weak star topology or not? And for here, I'll say on the trace space rather than on the state space. So in the classical case, every compact group admits a unique translation invariant Borel probability measure, i.e. the Haar measure. And in the quantum setting, we have a Haar state. And amazingly, Voronovich showed that every compact matrix quantum group admits a unique Haar state. And so that is also a really nice continued analogy with the classical case. And well, in terms of then seeing what we could do with our quantum metric, then we were able to obtain this result. We were able to look at how the quantum Hamming distance behaves under convolution. And so this looks promising. And so one of the ways in which Voronovich, well, the way in which Voronovich showed that each, the existence of a Haar state is that he did it by construction. And so taking this as our convolution product, he showed that if you start with any faithful state, then the Haar state can always be obtained as the weak star limit, no matter which one you start off with. And so then the natural questions for us to look into are, under what conditions does this, can we, could we metrize this convergence with respect to either of our quantum metrics? And what about when it's not faithful? Can we describe what the limit looks like of this? And can we determine whether, convergence occurs with respect to our metrics? And another related question is, how do the metrics behave with respect to convolution semigroups? And we would like to look at the one studied by Franz, Kula, and Skelski. And in the study of the trace space, one of the things one can study is like the extreme points on the trace space. And so combinatorially, how could we classify the extreme points that arise from the finite dimensional representation? So another thing about a lot of universal C-star algebras, like the quantum permutation groups, is that they admit a lot of traces. And so each of these finite dimensional representations in terms of the sort of matrix that that you can build a trace from that. And so how does the trace space relate to these different representations? And does it have the structure of a Bauer simplex or a Poisson simplex? And so this is a question that actually arose after, during the last workshop. So there was a presentation about doubly stochastic matrices, the Birkhoff polytope of them, and we wondered under what condition, like whether we could study such a structure in our setting, and so that was a question, because that came up in the course of this program, one that I wanted to point out. And I'd like to conclude on that, and thank you very much.